Hi, my name is Sabu Francis. I'm an architect. I'm from India. Long time back in 1987, I started my practice, and quite soon after that, I started using computers. And then I came up with one design software, an architect's design software called TAD. It stands for the Architect's Desktop. So, last few years, I've been conducting various workshops, seminars, and writing papers about this, discussing with my fellow architects, and I've been trying to explain the concepts of TAD. What I'm now doing is I am trying to explain TAD once again, but from the point of view of programming and artificial intelligence. Uh, One of the things which is happening nowadays is that a lot of people are talking about artificial intelligence, and one point which is often missed is that TAD is actually the oldest architecture design software with its own built-in artificial intelligence scripting system. It's called ARDELA, Architectural Design Language, a computer language which I invented, which is based on the popular AI language called Prolog. Now, I call it popular, but there are many people who think that it is from the age of dinosaurs. So there are some misunderstandings about artificial intelligence and why such design software needs to be written and why you have to use such a software. And I hope this particular talk will shed more light. I'll be doing this in two parts. One part I will give some amount of background theory, and in the second part I will actually give a hands-on demonstration of what I'm talking about. So, at the end of the second part, you should get to know how TAD really works and what would be the advantages of doing something like this. Before I start, let me make it very clear, because this is a perception which unfortunately comes across in some situations, that I'm trying to sell TAD to you. I'm trying to convince you of adopting a way of looking at architecture. That part is right, but I'm not selling this. This is a free software, and I'm trying to encourage and invite people to really go deep into this and debate what are the basic fundamental points which are getting raised here. And let me again make it clear that I don't mind if TAD is not the way to go about addressing those concerns which I've raised, uh, provided whatever other alternatives which are there has addressed the points which TAD is addressing. So, which is fair, I think. Anyway, so let me give a brief of how it all began, and I'll just start with uh, the next slide. And I think I've lost the webcam. It looks like 1 minute. Okay, so I was a associate for Hafiz Contractor, who is now pretty famous architect in India, and is one of the largest offices. It does a lot of commercial and residential projects, and he's pretty well known. There are many people who unfortunately do not like his approach. But as an architect, since I worked with him, I was his associate. At that time, there were only 8 people in his office. um, I've seen there's a lot of knowledge which this person has, this architect has, and there was a shift which was happening in India those days, where instead of very boring looking buildings, this man introduced a new way of looking at uh, design. Some people said that it's just superficial, skin deep, and all that, but really speaking, there was some very serious shift in the way architecture was being perceived in developing country like India. So that's a background. I left Hafiz around 87. Actually, I didn't fully leave him. I was an external associate for a couple of years more for a few of the projects which I was handling. This project, which you can see on the right, is the skyscraper which I was, the three skyscraper. This is one of them, which I was handling as an associate at Hafiz's office. And as you can see, it doesn't look like a modernistic building or anything like that. There is some necessity to go around playing with forms and things like that. My worry was that there was still mistakes which were happening, and I found it pretty contradictory. A very nice guy, very talented, very knowledgeable guy, but finally the works are not, quite often, not really up to the mark. And I realized that it is not the person which is really creating a problem, it is the way architecture was getting represented before you worked on it. And then whatever work which you did, the fault many times, quite often, it starts with the way you communicated that representation. You have to discuss and debate about that project, right? So there were inaccuracies there, and that is not really to do with just Hafiz. It is something which is plaguing our field right across for everybody, which is one thing which is sometimes a little difficult for people to digest, to say that. But truly that's what is going on, and that's the point which I'm trying to put across to fellow architects, that it's very important to really debate all this. Okay, let me not get pedantic about this. So this particular project, uh, this particular situation is when I started my practice, and somebody said that if you want to really go deep into um, computers and all that, I bought my first computer just a few months after I started my own practice, because I got convinced that maybe computers have an answer. Or I said, let me explore that at least. I did not know anything about computers, frankly. And so I took the DOS version of AutoCAD from somewhere, and this is a screenshot from the old DOS version. Some of you probably may not have seen this particular version. You have to use a keyboard. There was no mouse also those days, so you have to go with the cursor keys and start making drawings. One of the things which irritated me was this continuous need for selecting objects. Like if you ask for area of something, I've just drawn one shape, say a closed polyline, which is what many people do to represent, say, a room or something. And the moment I say give me the area of that, it'll say what area. Select the object, then I can. And I used to wonder, I just drew that area right there in front of you, and there's only one thing which is there. So why are you asking me to select the object again? So that means internally AutoCAD does not understand this, and AutoCAD does not understand the logic of it. I understand the logic, but AutoCAD is just understanding lines and circles and arcs and all that. So this was extremely dissatisfying. So I started working on my own algorithms and way of looking at architecture, and then I came up with TAD. So before I really talk about TAD, let me give you some more introduction about the basis on how these things start. This kind of thinking starts. One of the things which humanity does is that we have always making tools, right? We make a spade, we make a plow. So we are the greatest tool users and tool makers of all animals. I mean, there are a few animals which can use some sticks and things like that, but not to the extent which humans can do. One of the things which we need to observe is that we develop purposeful machines. So if I develop a spade, if somebody invents a spade, it has got certain very clear purposes. If I invent a plow, there is a very purposeful machine out there which gets invented. And in case something goes wrong, so now that man is plowing the land there, and if it turns out that some part of it breaks, what happens is that he's going to be focused on the problem which he can fully understand, because it's to do with the empirical evidence. He can extract and start debating about, should I get this repaired, should I go to the blacksmith, or should I do it myself. All those thoughts comes into his mind is based on the reality which is there in front of him, which is a broken plow or a broken spade or whatever, right? This started changing as society became more and more complex. So here it is on the left hand side, a simple world. You have a spade over there, and this person is thinking about that broken spade in case something gets broken over there. But as society became more and more complex, the range of things and this angle of vision which he or she has to extend, has now gone to pretty abstract layers, and also to the real world. So it's not as simple as saying that I saw one particular plow or a spade which got spoiled. I can see the broken parts there, and therefore I can take some decisions on that, and then repair that and come up with a better solution or invent a new thing. Now society needs you to go to a higher level of abstractions about trying to understand what is this particular problem, because there are lots of interconnections to different things. We have to understand what how the data about that particular problem is getting handled. There are so many other things which we need to consider, and then we can actually go and do something which will affect and improve things in the real world. So the angle of or the scope of things which a person has to do has actually got extended quite a lot. This has led to a kind of breakdown of the kind of work, or you can say there's a separation of concerns which has now happened. So the guys who talk about the problem statement and express that problem statement um, is sitting somewhere else. Like for example, the person who worked out the CAD software or the BIM software and all, almost nobody is an architect. It didn't come from architecture sources. Okay. And architects are somewhere else. The guys who talked about the abstract concepts and all are somewhere else. And actually, there is a real disconnect between these two things. Why am I pointing this out? Is because as architects, were trained to become inventors, right? Architects, frankly, is an inventor. We don't repeat the same design again and again and again, right? We think through right from fundamentals and then develop a design. So it actually should have got right into our skin, and we should have been working out, figuring out what is the problem which has to be solved, how do we create the right tools for it, and then go about solving it. But that is no longer the case. Things have become so specialized, so to speak, which is unfortunate, that there is disconnect between people who are actually analyzing all the abstract situations and proposing some solution, and the tool user. So the tool maker and the tool user has started becoming different. They got separated, and it has actually become like a given thing that, okay, I mean, what, CAD is a black box, I use it. Why should I care about how it was made? That's an approach which has unfortunately started happening. But when push comes to shove, and when you really try to put that particular solution into place, and then you find that deep down it is not really connected with the real world situation which we are in. The real world is still pretty complex. It was complex many years back, and many years back we were actually observing what is the problem we are doing. We were ourselves the tool maker, the tool assessor, and the tool repairer, and everything, and the tool user. And then that separation started happening. One of the ways, and I don't say it's all bad, there is a method in why this happened, and there's some probably different lectures about how society evolved about all these things. So here is another diagram which essentially captures the same thing, that we were taking problems and then directly working out the solution. But now we are taking a problem, going to an intermediate space where we hope to connect between what is the problem which we are facing and how do we reach the solution. Okay. And that indirect space started happening from the industrial revolution. You take the loom, for example. So people were working out the machinery or the intricacies of a loom, which will produce one kind of weaving. Then there were some French engineers And all these guys, they came up with an intermediate system where you start using a punch card, and so you have essentially the same machine, but then the thing gets shifted into the punch card, and the punch card changes the nature of what the solution is, so you get different designs essentially from the same machine. The only thing which changed was the programming of that loom. So you can roughly say this could be one of the precursors of a computer. Now this kind of abstraction became more and more, and now when we face a problem, we put it onto a computer, we put software into that, and the problem is assessed by that software, and then we start working on the solution using that software. So you're going through a roundabout route to get your job done. Why is this important for architects to know? Like I told you, architects were actually original tool makers along with tool repairers and tool users, right? I mean, just think about this. 300, 400 years back, what did an architect do if he have to really, solve an architectural problem, and if he has to represent it, he'll have to stretch the canvas himself, he'll have to even make the ink, grind the ink, okay, and he has to make the pen and all kinds of things. In fact, architects are, and if you can use that term for those intelligent people during the Renaissance, like Brunelleschi and Raphael and others, and they actually were talking about representation, how to make plans, sections, elevations, and one point perspective, 2 point perspective. There is an interesting book called The Dome, which talks about how Brunelleschi tackled the problems with the dome, the Florence Cathedral dome. And that was a very, very intricate part of architect's life, that we were rolling up our sleeves, getting our job done. What my point is that as an architect, we need to really look into this redirection which has happened, this purposeless machine which has started coming in. Effectively, a computer is purposeless if you didn't give it a software, right? It's a very crazy invention. We were earlier having purposeful inventions. Now we are talking about purposeless machine, which kind of takes up the coloring of whatever software you give, and takes up the capabilities which somebody who wrote the software thought it should have. But that person who wrote that software is quite often disconnected from your problem statement as an architect. You're relying on some software nerd sitting somewhere writing graphics program, and then you're thinking that is what you can also use. Okay, so I'm trying to shift that point. Okay, so this is a very interesting problem in computer science and in other fields, and it's got very direct reference to why should architects really get under the skin of software and computing, and now with artificial intelligence, uh, this kind of thing. We have to really start unraveling what is this all about, why do we need this. Okay, so let me describe this particular riddle. It is often given as a riddle in, I think, some high end job interviews, and all people ask this question, that say you are a blind person and you are put onto a landscape which has got some hillocks. Okay, and the only thing you have is that blind person stick, and using that stick you can sense where the next step which you are taking, is it going up or is it going down. And your task is to actually reach the highest peak, which is known as a global maximum. But there are other peaks also which are around in that landscape, which are not global, which are called local maxima, that somewhere a small hill is there. Now the problem is that if this blind lady is trying to climb this, she will sense with her walking stick and her footstep whether that particular next step which she's going to take, is it climbing up, is it going up, or is it going down. And if she finds that she reached a point where she's in any direction, if she takes the next step it is going down, it means she has reached some peak or the other, which is either this peak or this peak or this peak. Now, by her bad luck, she may have ended up on this peak. Now, how will she know whether is this really that biggest maximum which she has to reach? No, right? I mean, we observing it from outside, we are not blind. We are looking at the blind lady. We are observing it from outside, and we can see that if she gets stuck here, she will think that she has reached that peak, but actually she has not reached the global maximum, right? So look at it like this, that when we are trying to design any building or any piece of architecture, how do we know that the piece of architecture which we design is really the best possible in that given situation? Okay. So what has happened is society has thrown up all kinds of complexities which finally ends up on the shoulders of architects. One of the drastic things which I learned when my software was used in two research projects on energy calculations with IIT Bombay, and what they found, there are people who have done a lot of research on all this, that almost 40% of all the real global issues, you talk about energy usage, you talk about carbon footprint, you talk about sustainability, you talk about whatever, global climate change, all these issues, really speaking, can be drawn to architecture. And that's crazy, right? I mean, which architect will start designing something saying I have to create problems for the world? Like, so we are sitting down possibly stuck in some local maxima somewhere without realizing that maybe a few steps here and there and we could have reached a global maximum. So there are certain recommendations which I'll get into later on why and how you should do. I'm trying to explain the why. How you can do that, one obvious thing is that you have to try out many different things, which means it has become really tough. As it is, trying out one design is going to be a problem. Now to try out multiple designs is what I recommend. It's known as abductive logic. So you have to assess between various designs which is getting proposed, and then see whether have you reached that global maximum between those projects. Otherwise we can happily get stuck in one little local maxima and never really reach our best, which may be a few steps away actually. So this is the reason why it is important for architects to really get under the skin and to understand what on earth is computing about. Are we simply looking at all this as black boxes and say, okay, just do that? Now, I mean, they have worked it out. What are we getting involved in it? Somebody has worked it out. Okay, it is not like that. You have to really start unraveling and checking, and that has been something which is lacking not just in architecture, it's been happening in many other areas also, right? For example, the usage of plastic came as a byproduct of the petroleum industry. Didn't somebody take a calculator and say that I've got a plastic bottle manufacturing plant, it is producing 2 million plastic bottles a month, and these plastic bottles don't degrade, so he just has to take a calculator and figure out that if he's producing 2 million bottles, his factory, what will happen after a few years? How many millions of bottles will be hanging around? Somewhere or the other it has to hang around, right? So if somebody who really could have worked on it, they could have arrived at this and started panicking, but they're all probably stuck at their own local maximas, and they didn't think that a global maximum need to be achieved. So now the problem has gone berserk and gone out of hand. So that's just one of the examples. So when I tell architects that even good architects end up doing terrible things, is a possibility at least we should need to consider. If it gets eliminated, fine, but what if you didn't consider that and you got stuck in archaic ways of looking at your projects before the project came up, which is that area which I've been really been researching for years together, and then you end up with a mess. What are you going to do? Okay, so let me go to the next slide. So that is how you have to start understanding the why of programming. Okay, so programming started, actually computer science is a very young field. It is probably about 80 years old if you measure it from the time of Alan Turing. There were a few events before that, Charles Babbage and uh, all those people. There was this machinery for carrying out the survey in US, census, sorry, sir, the census had to be taken, and so there was some landmarks or milestones in computing. But the real milestone which practically everybody agrees to is what Alan Turing does, which is captured in that movie, The Imitation Game. And if you have not watched it, you must watch it. It is reasonably accurate. And from that time, if you start measuring the time span, so computer science is a very young field. And when they said that we need to go into abstractions to understand the thing, one way of doing it by programming is to give every little instruction step by step. It's like, telling a small child what he has to do if some guests are coming to your house. So that's one way to give instructions. Okay, so this kind of programming, so a lot of programming languages fall in this category. Even today, they fall in this category. In fact, bulk of the programming languages fall in this category, where every little thing which has to be done to solve the problem is described step by step. It's like holding a person by his finger and saying, okay, you have to do this first, then you have to do this next, and then you have to do this next, like in that example which I've given here. So if some guests are coming, so you say, okay, here are the resources, here is 100 rupees, you have to buy milk, you have to buy tea, you have to buy biscuits and a wiping cloth. Then after buying all that, come back home with the purchased items. Then you have to wipe the dining table, then prepare the tea, you have to boil the water, add leaves, whatever, all that, and then serve the snacks, and then wait for the guests. So what you have done is that you have explained the procedure for addressing a particular concern. This kind of programming is done in many computer languages. A lot of computer languages still today uses this approach, where everything has to be described in some form or the other. It gets described. This kind of computer languages are called imperative language. It's saying that it is imperative that you listen to me. It is the programmer is telling the computer that you better don't apply your brain. I will tell you what you have to do. You please do it exactly the way I'm telling you. Okay, so these are all called imperative computer languages. A lot of them fall under this category. You take Python, you take uh, Pascal, you take C, C++, Java. All this broadly comes under imperative programming style. You cannot miss any step, and you have taken the responsibility. The programmer has taken the responsibility for getting that particular work done. Now imagine this: you're an architect, you have faced some problems, but the actual assessment got done by some people sitting in some IT company, Autodesk company, or wherever, and they are imagining what is the problem which you have. They have not really sat and discussed with you, right? And they sat down and thought that this should be the procedure, which finally I'll write the software for this, give it to the architects. They will then start utilizing that. The architect feels damn thrilled because somebody did all the work and now we have to just use it. My point is, we have to now start criticizing that. Why so? Because it was not just me. In fact, artificial intelligence started with this bunch of gentlemen you see here. A few of the names I've written here. John McCarthy, he's the inventor of an AI language called Lisp. Marvin Minsky is a big guru in artificial intelligence. He's also the person whose work was finally used in VR headsets and all that. Finally, you can trace back to this person's work. Claude Shannon is a big guy. In fact, he's the father of a whole branch of science called information theory, and a lot of computer science is based on the discoveries and the theorems proposed by Claude Shannon. So these people were getting together and they were asking kind of a similar question, that can a computer's efficiency be improved? Okay, because you are actually sitting down and describing everything. right, and giving it to the computer. So the computer is just sitting down like a dumb slave and figuring and doing things because you said it to do, it is doing that. They said that, can we start adopting some principle? Those days they thought that there is some principles they could discover about human intelligence, and then start figuring out, can a computer be made to use that kind of intelligence? That is when they were, I think John McCarthy proposed this group of people to get together at Dartmouth College, and he had to sanction the budget for that get together. It was a workshop conference for a few days, so money has to be procured, so it has to be titled. That is where the word artificial intelligence got invented, which is rather unfortunate, because the real reason why they got together was to say that, how can computers do a better job? Okay, can they solve problems which the way humans can solve? Okay, from a very innocent point, not from any dramatic point of view. I mean, why are we sitting down and talking about each and every little step? So this is where artificial intelligence really started. In 1972, there was a breakthrough. That's where I would consider. So there are other breakthroughs which happened, but since I worked on a particular line of thought, I am skipping the other steps, and now I am talking about a very important breakthrough which happened in France. And they came up with another way of looking at it, which is where you declare what do you want to achieve to a computer. You don't go around talking about each and every little step, like, oh, OCD, do this, buy that, do that, do this, and then come here and then wipe the dining table. Nothing. So they said that the same problem could be addressed as a set of goals and sub goals. So you say that you call up human. I mean, this is what we will normally do with humans. We don't do it the other way unless you are a very hard case taskmaster and you don't trust the guy whom you are giving the instructions. There you have to give imperative instructions. Here, what you do is you tell what goal you want to achieve. So you say, we have guests coming, okay, so we should treat them well. That's the overall goal which we have. So we have to provide some tea and biscuits, because that's what it means to treat somebody well. Okay, that's one of the ways by which we say. And we have to ensure that there is a clean table. And here is 100 rupees. Now you do what you want to do so that these sub goals and the eventual goal of treating the guests well gets achieved. This form of declarative way of telling what needs to be done is what these gentlemen, Alan Colmerier and Robert Kowalski, I'm sure I'm not pronouncing their names correctly, they discovered this computer language called Prolog. And I've been kind of very deeply involved in Prolog for now more than 30 years. And I actually wrote my own version of Prolog, which is called ARDELA, Architectural Design Language, which is embedded inside TAD. So this is where we are in this first part of this particular talk, where I'm trying to build up the reasons why an architect should get into that abstractions also and figure out what type of programs are we really dealing with today, because there is so much amount of misinformation, hype, hubris, generative AI and chat gpt and magical things happening, that we are forgetting some basic fundamentals of what artificial intelligence really is. So I think in this part is what it is. I hope it is good enough. I will come up with the second part. Thank you very much. I hope you will be there for the second part also. Thank you.